Welcome back, dear students. Today we are going to discuss a very special problem in which fluid mechanics is coupled with rotational motion concepts and the buoyancy concept. So it is going to give you a very good insight in the problem of fluid mechanics and rotational motion. So the question says there is a closed tube of length capital L completely filled with water and has a small air bubble trapped in it. So this is the tube and its total length is L, and when the tube is held at an angle theta, and rotated at a constant angular velocity omega about the vertical axis, so it is rotating something like this, okay, through the lower end. The bubble settles at some intermediate position in the tube. So bubble is at equilibrium in this position, and let us say its distance from lower end is small l. Okay. So question is, what fraction of the eta of the length tube is the distance of bubble from the lower end? This is our question. So we have to find the value of neta, which is L upon L. Okay. What is it? Neta, which is small l upon L. This we have to find. So let us see what are the basic concepts involved in the question. This is the scenario and it is rotating. This angle is theta. Now suppose this tube was not rotating, then what do you think where this bubble would have been? Definitely because of the buoyancy force, this bubble would have rised up and would have settled it somewhere here, okay, in absence of rotation. But what happens when rotation is there? When rotation is there, you just see what is happening. Let us take a very small water element here. This is the water element, suppose say. It is rotating in the circle. I mean something like this, it is rotating. So what is happening? This water element is feeling what? A centrifugal force of radially outward. What is the magnitude? M omega square r. R is what? R is the radius of path of this water element. This is r. That means you say because of this centrifugal force Fc, let us call, the water is feeling some pressure, isn't it? Some radial pressure this water is feeling, and this radial pressure goes on decreasing as you go down because R goes on decreasing. Here it will be something like this, here it will be some lesser, here some lesser, here some lesser, and finally here Fc is equal to 0 because radius is 0 at this point. That means you see the centrifugal pressure is maximum at this point. Here centrifugal pressure is maxima and here the centrifugal pressure is minima. That means the pressure gradient is in which direction? Centrifugal pressure gradient is from top to bottom. So this pressure gradient does what? It pushes the bubble downward, okay, something like this. So this is because of the centrifugal radial pressure, and this is because of the buoyancy. So buoyancy component this side and centrifugal component pressure this side, these needs to be equal so as to ensure that the bubble remains here. So this is the essential concept. Now if you wish, you can try to attempt the question on your own because the concept I have told you. In order to give you a better and clear mathematical picture of rotating fluid, let us say this is the scenario and there is a tube of cross section A and it is filled with water and it is rotating with angular velocity omega in a horizontal plane, okay. So let us see how the pressure varies. I am just giving you to give a picture of what happens in the rotating fluid. Suppose we take some element, this is the center O, and we take a small element at radial distance r, let us say dr, okay. So if you see the centrifugal force on this element, what it will be? Let us call df the centrifugal force. It will be what? Mass of the element dm omega square times what? R. R is the radial distance, okay. This is the centrifugal force on this. Now dm is what? Dm clearly, dm is equal to mass of this element, which is rho a dr, rho dv, a dr is the volume, so dm is this. So df, what you can say? Df is rho a omega square r dr. Okay. Now you see, if you want to find the centrifugal force on this face, let us say this cross section, let us call this cross section C. Okay. If you want to find the centrifugal force of the whole water lying in this part on this cross section, it will be what? It will be simple integration of this fraction, this equation, from where? From r equal to 0 to r, and this 0 to f. So what you get? You get centrifugal force is equal to what? Rho a omega square r square by 2. Okay. Now what is pressure? Centrifugal pressure, if we talk about, centrifugal pressure is force upon area. Area cross section is this. So centrifugal pressure is nothing but rho omega square r square by 2. This is the radial centrifugal pressure, and this is, you see, it varies as a square of r square. I mean, it varies as a square of r. That means if you plot the pressure profile, it will go something like this, isn't it? So centrifugal pressure is maxima at radially outward point and minima at the center. That means pressure goes on decreasing as we go from outer periphery to inside. So suppose some bubble is here. This bubble will be pushed inside because of the pressure gradient. So same is the situation here. This bubble will feel a centrifugal pressure gradient force, let us call Fr. Okay. Here also this is the centrifugal. So this is the essential pressure, this essential force which is trying to push back the bubble. So now let us see how to analyze this question further. So we have finalized that on bubble two forces are acting. One is the centrifugal buoyant force, let us call Fr. Other is the normal Archimedes buoyant force, let us call Fb. Okay. Now these two must be equal so as to hold the bubble in equilibrium. So let us equate these components. If this angle is theta, we can clearly say what? We can say that if you see here, this angle is theta, so this angle is also theta. And we have to, for equilibrium, what we need? We need Fb cos theta should be what? Fr sin theta. This should be satisfied. Now, here comes a very important and turning point in this question. What do you feel? How can we find Fr? This radial buoyancy force, this centrifugal buoyancy force, how can we find? Do we need to integrate? I mean, as we did in the last part, do we need to integrate and find it through a lengthy process? So as we can put it here and we can find the ratio. I am going to tell you a trick in which you are not supposed to do all this lengthy process and you can directly come to the solution. Let us see how. What you do, you take this bubble as a free body diagram. I am taking it out and drawing it as a free body diagram. What are the forces acting on it? Let us see. This is what? Fr, that is the centrifugal buoyant force, radially inward, and this is the Fb, that is the normal Archimedes buoyant force. What are the other two forces? Because it is rotating, so it will be feeling a centrifugal force m omega square r, where r is what? R is the radius of the path of this bubble. Okay, this is r. This path on which the bubble is rotating, its radius is r. Okay, and other force what? Weight of this bubble, mg. Here m is the mass of the bubble. M is mass of bubble. Okay, Now you see how easy and simple it has become. You just simply see, as it has to be in equilibrium, we can clearly say Fr should be m omega square r, isn't it? And Fb should be mg. So put it here. Fb is what? Mg. That put it here. What you get? Mg cos theta is equal to what? Fr. Fr is what? M omega square r. M omega square r times sine theta. Okay. So m and m get cancelled, and what you get? You get r is equal to what? Or here you draw the triangle. I mean, suppose this is the rotation. I mean, this is the axis and this is the tube. So it is aligned something like this, and somewhere here is the bubble. Okay. Now this is the R, and what is this? Let us call it capital R. So, and L is this distance. This, as we have already seen, L is this distance, and complete tube length is what? Capital L. Complete tube length is capital L. So from the similarity of triangles, we can very easily say that L upon L is nothing but R upon R. Okay. So what, and that is the eta we have to find. So we can write small r equal to eta times capital R. So let us write g cos theta is what? G cos theta is omega square sin theta times small r is r, neta times r. And r, you see from the bigger triangle, r is what? R is nothing but L sin theta. L sin theta. So put that. So you get g cos theta is equal to omega square sin theta r what? L sin theta times neta. That means neta you get what? Neta you get simply g cos theta upon omega square L sin square theta. This is the value of neta we get. So you see how simple it becomes if you simple apply the equilibrium motion and the equilibrium concept. So this is our final answer. G cos theta upon omega square L is the length and sin square theta. Hope you have understood the solution and understand the concept. So if you have any doubts, any queries, any questions regarding this, please feel free to ask in the comments. Thank you.